Page 776, lesson 12.8 is on probability of compound events. So a compound event consists of two or more events. So if there's at least two things happening, we can call it a compound event. For compound events, some of them could be mutually exclusive. Mutually exclusive means they don't have any outcomes in common. So for example, if we are rolling a number cube and they want us to find the probability of an even number or a 5, even number or a 5, 5 is not an even number, so those are mutually exclusive events. Another possibility would be we could have something called overlapping events, or you could call them not mutually exclusive. If they have at least one thing in common, they're overlapping or they're not mutually exclusive. So an example of that with the number cube again, if we talked about the probability of an odd number or a prime number, so if you think about odd numbers and prime numbers, odds would be 1, 3, and 5. And then 3 and 5 are also prime numbers. So there's an overlap there. So those are overlapping or not mutually exclusive events. So this is what we're going to be looking at when we talk about finding the probability of something or something else. Probability of A or B, and they can list it like this: probability of A or B. What we're going to do for the probability of A or B is we're going to add our probabilities. There's only one thing happening, so we're just going to look at all together what's the chance of this thing or this thing happening. When we do that, we want to make sure that we don't count the overlapping events more than once though. So we'll talk about different ways you can do that. The book shows you one way. I'll mention a different way just as another option for you. So the book talks about if they're mutually exclusive, if there's no overlaps, you can just add their probabilities together. They're separate, no overlapping, we just add the probabilities. If there are overlaps, if they're overlapping events, then you can add the probabilities and then subtract the part that overlaps. Okay, that's that last part there, they're subtracting the overlaps. And again, the other option you have is to just list out all the possible outcomes and then just make sure you don't count the same thing twice. Okay, so we'll talk about that in a minute. I think it's a little simpler listing things out than adding and then subtracting from that, but that's up to you how you want to do these problems. So if you look at problem 1, suppose you spin a spinner that has 20 equal sized sections numbered from 1 to 20. What is the probability you spin a 2 or a 5? So a 2 and a 5, obviously there's no overlap, either it's a 2 or it's a 5. Probability of getting a 2 would be 1 out of 20. Probability of getting a 5 would be 1 out of 20. We want the probability of a 2 or a 5. We'll take either one of them. So we just add those together. That's 2 out of 20, or we can reduce that to a 1/10, or if you wanted to say a 10% chance of spinning a 2 or a 5. Part B, what's the probability you spin a number that is a multiple of 2 or 5? So multiple of 2 or 5, if we list out the multiples of 2, we've got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Multiples of 5, we have 5, 10, 15, 20. And again, just little different way than what the book's showing you. if we want a multiple of 2 or a multiple of 5, what we could do is, notice the 10 and the 20 were multiples of 2 and multiples of 5. We just want to make sure we don't count them twice. Okay, so one way of doing this is we can just count these up. We got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 multiples of 2 here. And then 2 more multiples of 5 that we haven't counted yet. That's a total of 12 out of 20. And that reduces to 3/5. The other option, what the book's showing you, is their definition that they showed on the other page. They said there's 10 out of 20 that are multiples of 2. There are 4 out of 20 that are multiples of 5. And then there are 2 that are overlaps that we subtract out because we don't want to count them twice. So it's up to you how you want to do it. Like I said, to me personally, I think it's maybe easier just to write out all the possibilities and just make sure you're not counting something more than once. But if you'd prefer doing it the way the book shows, with adding and then subtracting from that, you're welcome to do it that way as well. So if we look at the got it 1, suppose you roll a standard number cube. What is the probability you will roll an even number or a number less than 4? So for an even number, we could have a 2, 4, or 6. And then the numbers less than 4 would be 1, 2, or 3. So we're just looking at overall what are chances of one or the other thing happening here. So again, you can either do it the book's way or do it the other way that I mentioned. So like the way that I showed you, if you want, you could say 2 appears on both lists, so we just don't want to count it twice. Basically, then we could have a 1, 2, 3, 4, or 6. Okay, these are our different options that would work, and that's a 5 out of 6 chance. If you did it the way the book was suggesting, that would be a 3 out of 6 plus a 3 out of 6 minus, there was one that showed up on both lists, one overlapping section, and you'll get the same answer that way also. So again, it's just kind of a personal preference, which way seems easier for you to work that out. So if we look at part B, they want us to find the probability of rolling a 2 or an odd number. So probability of a 2, our only option there is a 2. Odd numbers, we could have 1, 3, or 5. And so overall we've got 1, 2, 3, 4 out of 6 options. And we could reduce that down to 2/3. So if we look down below that, we're going to talk about independent events. Independent events, this is what happens if the occurrence of one event does not affect the probability of the second event. So for example, if we're rolling 2 different number cubes, what I roll on the first number cube isn't going to have any impact on what I roll on the second number cube. Basically with what's happening here, this is the probability of this and this. we have actually two things happening, okay? Remember the last thing, we only had one event, okay? With what we've already looked at, there was one event. We're looking at all together, what's the chance of this thing or this thing happening? With this, there's two things. Probability of this and this. So there's two things. We're gonna do this first, like we're gonna roll this number cube first, and then we're gonna roll this number cube second. And so what happens with that is we have to multiply the probabilities together. Okay, so when you see the word and, that means you've got more than one thing happening. We've got two things happening here. And so we're gonna multiply the probabilities. The more things that we want to happen exactly in a certain way, the less chance of that thing happening, okay? Like for example, winning the lottery or something like that. If you have to have all these things line up exactly, your probability is not gonna be very high at all. So if you look at problem 2, suppose you roll a red number cube and a blue number cube. What is the probability you will roll a 3 on the red cube and an even number on the blue cube? So first of all, the probability of rolling a 3 on the red cube is 1 out of 6. And then probability of rolling an even number on the blue cube is 3 out of 6, or 1/2. If we want both of those things to happen, we have to multiply their probabilities together. So probability of a red 3 was 1/6. Probability of an even blue was 1/2. If we multiply those together, we get 1/12. So there's a 1/12 chance that both of those things would happen. So we're going to look at the got it. So same idea, we're rolling a red number cube and a blue number cube. So we want probability of a 5 on the red cube and a 1 or a 2 on the blue cube. Okay, and they could list it out something like this, I guess. They could say probability of 5 and a 1 or a 2. So probability of a 5, there's only 1 out of 6 sides that are a 5. And then a 1 or a 2, that gives us 2 options out of 6. We are going to be multiplying these together. Before you multiply, if you want to try and reduce your fractions down, you can. 2/6 reduces to 1/3. And then if we multiply those together, that would be a 1 out of 18 chance. So if we look at problem 3, you choose a tile at random from the game tiles shown. You replace the first tile and then choose again. What is the probability you choose a dotted tile and then a dragon tile? And they're calling these the dotted tiles, if you can see. They kind of look like some stove burners, stovetop burners. Okay, so the dotted tile, there's 4 dotted tiles altogether there. And the dragon tiles, there are 3 of those, or 1/5. 3 out of 15 reduces to 1/5. And multiply those together would be a 4 out of 75 chance. This is called selecting with replacement because it says we're choosing a tile and then replacing it and then choosing again. So with replacement, we pick one and then we put it back and then we pick another one, okay? So in this case, by replacing it, it doesn't really affect our probability. We'll talk about something else later. Without replacement is going to be a little bit different. So if you look at the got it, in problem 3, what's the probability you randomly choose a bird and then after replacing the first tile, a flower? So the chance of picking a bird, there are 2 birds out of 15. Chance of picking a flower, after we put that one back in, there's 1 flower out of 15 if we put the first one back in. and then we're going to multiply those together. So that comes out to 2 out of 225. And again, we could divide it out if we're interested. It would be maybe 1% chance, slightly under that, if we work that out. Next thing we're going to talk about is dependent events. Dependent events is where one event affects the probability of the second event. So for example, we just looked at choosing tiles. If we would not replace the first tile and then we picked another one, then that's going to change the possible outcomes for the second thing that we get. And even if it's, like that last problem we looked at, choosing a bird and then a flower, even if we picked a bird, and you might say, well, if we take that out, that's not going to affect how many flowers there are. That's true, it's not going to affect how many flowers, but it's going to affect how many total tiles are still left. So our denominator would be changed, if nothing else, if we have a dependent event. So look at problem 4. Suppose you choose a tile at random from the tiles shown on problem 3. Without placing the first tile, you select a second tile. What is the probability you choose a dotted tile and then a dragon tile? So a dotted tile, there were 4 out of 15 dotted tiles. If we don't put that back in, picking a dragon tile, there are still 3 dragon tiles, but now if we kept that dotted tile out, we actually only have 14 tiles still altogether. So for that then, we multiply those together, and we could see that would be a 2 out of 35 chance of that happening. So if we look at the got it 4, what's the probability you'll randomly choose a flower and then without replacing the first tile, a bird? So we want the probability of a flower and a bird. Okay, and again, this is without replacing the tile. So looking back on the previous page, there's 1 flower out of 15. If we don't put that one back in, we still have 2 birds, but instead of 15, we would only have 14 tiles left. Again, once you get to that point, if you want to, the 2/14 we could reduce down to 1/7. So that works out to 1 out of 105. So again, a little bit less than a 1% chance of that happening. So before we go any further, just to mention a different problem. This is in my book, it's not in your book. We're going to do the same thing without replacement. So let's say we want the probability of a flower and a flower without replacement. So to start with, there's 1 flower out of 15. And then if we don't replace it, there was only 1 flower there to start with. So now we have 0 out of 14. If you multiply that, 1 times 0 is 0. So you're going to have 0 out of something. Doesn't really matter. 0 out of anything is going to be a 0. So no chance that we're going to pick 2 flowers if we only have 1 flower to begin with, without replacement. So if we look at problem 5, 1 freshman, 2 sophomores, 4 juniors, and 5 seniors received top scores in a school essay contest. To choose which 2 students will read their essays at the town fair, 2 names are chosen at random from a hat. What's the probability a junior then a senior are chosen? Okay, so the junior, first of all, we would want to look all together. So we had 1 freshman, 2 sophomores, 4 juniors, and 5 seniors. So if you add that together, that's 12. So we have 12 students. So we want to pick a junior and then a senior, see what would happen with that. So junior, there were 4 juniors out of 12, and that reduces to 1/3. And then to try to pick a senior, there were 5 seniors. We've already picked 1 junior out. So it's 5 out of 11 students that are seniors. And then if we multiply those probabilities together, that would be a 5 out of 33 chance of picking a junior and then a senior. So if we look at the guide at 5, going off of that same problem, they're asking what's the probability a senior and then a junior are chosen. So the probability of a senior would be 5 out of 12. Then the probability of a junior would be 4 out of 11. Even though you can't reduce each individual fraction, since we're multiplying, if you want to reduce the 4 and the 12 down, you can. If you don't reduce, you can reduce afterwards. But anyway, that works out to be a 5 out of 33 chance. So then part B is the probability of junior then senior different from senior then junior. And so looking back to what we just did in the last problem, that one also came out to be 5 out of 33. So is it different? No, it's not different. And we could explain that. Basically we're doing the same stuff just in a different order. It's not going to affect our probability. So we'll look at a few problems on your lesson check. So starting with number 1, you choose a card at random. What's each probability? So for 1A, probability of a B or a number. So we don't care if it's a B or if it's a number, either one will work. So if you look, we've got a B, we've got a 1, we've got a 5, and we've got a 10. So B, 1, 5, 10. That's 4 options out of 5 total. So 4/5 chance of that happening. Part B, probability of a red or a 5. So for that one, these are supposed to be red. So we've got 1, 2 reds and 1 5. So that's a total of 3 out of 5. Part C, probability of a red or a yellow. So we have 2 reds, we have 3 yellows. That's 5 out of 5 or 1, we can say. 100% chance we're going to get a red or a yellow. And then part D, probability of a yellow or a letter. So if we look at this one, we've got 3 yellows. And then we have 2 letters technically, but one of them was already accounted for. So we could just say altogether, we've got 4 out of 5. The other thing, like the book mentioned, you could say it's a 3 out of 5 plus 2 out of 5 minus 1 out of 5. If you want to go that route, you get the same answer. Number 2, what's the probability of choosing a yellow card and then a D if the first card is not replaced before the second card is drawn? Notice on this problem the word and means we have 2 things that are happening. So to start with, we've got a 3 out of 5 chance of getting a yellow card. I think that's not good in soccer, right? I guess we're not playing soccer, so we're okay. And then a D. And again, we're not replacing this card. So we picked a yellow card, now we're going to try and get a D. So if you want to, for this part, just imagine you picked one of the yellow cards. If you want to cross it out, you can. And then think about from that point the chance of picking a D. So a D, we've got 1 out of 4 that are left. And then we can multiply that together. So that would be a 3 out of 20 chance. Look at number 3. What's the probability of choosing a yellow card and then a D if the first card is replaced before the second card is drawn? Okay, so this time we're replacing the card. So probability of a yellow would be 3 out of 5. We put it back in. Now we've got a 1 out of 5 chance of getting a D. So that would be altogether 3 out of 25. If you go back on the last problem, we did the same thing, only we didn't put the card back in. So not putting the card back in, we actually had a 3 out of 20 chance. When we did put it in, now we had a 3 out of 25 chance. So it kind of just depends. We did the problem with the flower earlier where we didn't put it back in and we didn't have any chance. So it can just go either way as far as if you're going to have a higher probability or lower probability based off replacement or not. All right, so if we go over to number 7, describe and correct the error in calculating the probability of yellow or a letter from exercise 1, part D. So we just did a little bit ago, yellow or letter, and we came up with 4/5. They came up with 5/5 or 1. So the problem with what they did is that they didn't take out the overlap. So we had the letter B, that was a letter and it was yellow. We can't count it twice. So if they would have subtracted 1/5, that would have been okay. Or like we did earlier, you can just look at all the different options that work and just add them together. So this gives you an idea of how to work with probability of compound events. Have a good day.